Okay, let's unpack this. If you're following the AI world, you've definitely seen this massive trend. Large language models, LLMs, and their multimodal cousins, the
Yeah.
LVLMs, well, they aren't just chat interfaces anymore.
No, not at all. They're being shaped into these specialized AI agents.
Right, like autonomous software engineers or document drafters. And maybe most relevant for a lot of us, this promise of an autonomous data science partner.
And that promise is,
Yeah.
well, it's huge. The core idea is that these agents can operate pretty independently, right? Take complex instructions, tackle real-world data tasks.
But the central question, I think, for anyone actually relying on these tools or thinking about it is how close are they? How close are these AIs to, genuine data science expertise?
That's exactly it.
And that is really our mission today. We are taking a deep dive into a new benchmark, a really rigorous one designed specifically to answer that very question. It's called DSBench. Our sources come straight from the paper that introduces this test, and it's comprehensive, pulling material from these high-stakes, real-world environments. We're talking model-off competitions and Kaggle.
Yeah, the big leagues for data tasks. And this is where it gets really interesting, like right off the bat. Because the immediate takeaway, you just can't avoid it, it's kind of startling.
Which is?
That the state-of-the-art models, LLMs, LVLMs, the agents built using them, they struggle. I mean, significantly struggle with these realistic challenges.
So the performance isn't there yet.
Not even close, really. We're seeing performance levels far, far below what you'd call human expertise.
Okay, so to really get why these DSBench results are such a big deal, we probably need to understand what was wrong, or maybe just inadequate, about the older ways of testing AI in data science.
Exactly.
We had benchmarks like DS1000 or the math benchmark. They were useful, right? Stepping stones.
They were definitely stepping stones, but fundamentally you could argue they were testing the wrong things, or maybe just not enough of the right things.
How?
Well, previous evaluations often focused almost exclusively on pretty simple code generation, or maybe basic math problems.
Oh, okay.
The tasks themselves were usually brief, often constrained to just one modality, typically just text.
Right?
And sometimes, they only needed a few lines of code, or maybe just a single step of reasoning to solve very contained problems.
So too much focus on just syntax, like can it write code that runs, and maybe quick fixes rather than the strategic thinking.
You've hit it exactly. They weren't really testing that high-level strategic ability needed to, say, scope out and solve a completely novel data problem.
Hmm.
And the researchers behind DSBench, they highlight this critical gap. They say real-world data science is, and I like this term, tool irrelevant.
Tool irrelevant, meaning
Meaning the goal isn't just about writing perfect Python syntax or nailing an Excel formula. It's about strategically applying whatever tool makes sense.
Hmm.
Python, R, MATLAB, maybe even complex spreadsheet stuff to get insights from the data.
so the how is less important than the what and why.
Precisely. And these real tasks are intensely data-centric. They often involve really lengthy, complex instructions. You need deep contextual understanding. You need multi-step execution plans. It's messy.
It sounds like the old tests were maybe testing a clever intern, but DSBench wants to test a seasoned senior analyst.
That's a great way to put it.
Yeah.
Exactly. They needed that complexity, the length, and the real-world messiness.
Okay, so DSBench steps in to be that real-world litmus test. What's the actual scope? How big is this benchmark?
Oh, it's substantial. It's got 540 unique tasks in total.
Wow, okay.
And these break down into two main, pretty high-stakes categories. 466 are focused on pure data analysis tasks, and then another 74 are full end-to-end data modeling challenges.
And the sources pulling from ModelOff and Kaggle, that brings some serious weight. But they test different scales, right?
Absolutely, they do. And that difference is actually key to why the benchmark is so rigorous. ModelOff, that's all about global financial data analysis.
Right, spreadsheets, precision.
It's exactly. Precision, financial literacy, meticulous auditing. Often the solutions involve complex spreadsheet functions or, careful logical steps. Kaggle, on the other hand, that's the big stage for machine learning competitions.
Prediction, models.
Yeah, a different kind of strategy altogether. Probabilistic thinking, designing models, tuning hyperparameters, optimizing predictions. It's a different beast.
So by pulling from both, DSBench is testing if the AI can be both, like a super precise financial auditor and a creative predictive modeler.
Correct. It's testing breadth as well as depth. Now, let's talk about the features that make DSBench genuinely challenging compared to those older benchmarks.
Okay.
First off, the complexity just starts with the context itself. The average length of a task description in DSBench, get this, It's nearly 800 words, 797.9 to be exact.
800 words just for the instructions. That's huge compared to what, like DS-1000?
DS-1000 was averaging about 140 words.
Wow.
So yeah, that massive difference alone is designed to really challenge the model's ability to just parse out what's relevant. It forces them to filter signal from noise.
Okay, so long context is key. What else?
Second big thing, DSBench is highly multimodal. Tasks aren't just a block of text. They include text, sure, but also tables, images, and crucially, actual data files, Excel, CSVs.
Real files they have to open and work with?
Exactly. The agents have to handle reasoning with potentially large data files, sometimes multi-table structures. It mimics the messy data sources we all deal with day to day.
Okay, let's dig into those two task types a bit more, starting with the data analysis part, the 466 tasks from ModelOff. What's the main goal there?
These are all about precision. The objective is answering specific financial data analysis questions. They're typically multiple choice or fill in the blank.
Sounds simple enough.
But getting the correct answer requires really full contextual understanding of all the data they provide and grasping the precise intent behind the question. Nuance matters hugely here.
Can you give us that concrete example you mentioned, the Excel stand election scenario? Walk us through why that's such a hurdle for an AI.
Right, the Excel stand example is perfect. So imagine the agent gets this raw data file, maybe a spreadsheet, with details for 1,000 voters across, say, 9 different districts.
Okay.
Each district is defined by a specific range of district codes. Now, the question might be something like, how many voters are in the Delta district? And the instructions specify that the Delta district means codes 135 through 144.
Okay, seems straightforward for a purser. You just open the file, filter.
Exactly. A human analyst knows immediately. Step 1, find the voter file. Step 2, filter it. But for the AI agent, this is actually a complex, multi-step cognitive challenge.
How so?
Well, step 1, it has to interpret the textual context, the 800 words, to even locate the correct data file. Step 2, it needs to load that file, which might be big, maybe multiple sheets, into some kind of runnable environment, usually using a tool like Python's Pandas library.
Okay, it needs to.
Right. Step 3, it has to write the specific code to filter that data. So district code greater than or equal to 135 and less than or equal to 144. That logic needs to be precise.
And then execute it.
Step 4, execute the code and output the exact numerical count. The ground truth, the correct answer is 115. The AI has to maintain that whole strategy, correctly use the tools, handle the file I/O, interpret the text, and get the number right. Any slip-up breaks it.
Okay, yeah, that makes it way harder than just generating a little code snippet in isolation. Got it. So moving to the other side, the data modeling tasks from Kaggle. This is where the AI has to prove it can build predictive models.
Exactly. This is the full end-to-end machine learning challenge. It's not just writing code. The agents have to actually design a suitable model architecture.
Design it, wow.
Yeah, then implement the training code, the testing code, and finally generate the actual predictions on unseen test data, just like in a real Kaggle competition.
Okay, but evaluating ML models, there's so many different metrics, right? AUC, F1 score, mean squared error. How did the researchers create one single score to compare agent performance across all these different types of problems?
That's a really important point. And they came up with a clever solution, a custom metric they call the relative performance gap, or RPG.
RPG. Okay, how does that work?
So because every Kaggle task uses a different evaluation metric tailored to that specific problem, they needed a universal yardstick. Think of RPG as a normalized score. It basically tells us how much of the gap between a really simple baseline model, like predicting the average, and the best possible performance, often represented by top human scores, the agent managed to close.
Ah, I see. So a high RPG means the agent performed much better than a naive guess and got closer to the human or theoretical best. It lets you compare, say, a financial risk model's performance against an image classification model's performance fairly.
Precisely. It normalizes the comparison across this hugely diverse set of ML problems. A high RPG indicates genuine progress towards that human benchmark on that specific task, whatever the underlying metric is.
So DSBench puts these state-of-the-art agents through this really tough, realistic gauntlet. What did it actually reveal? What were the numbers? How did they stack up against humans?
Well, this is where it gets, as I said, alarming. The results show this massive, just undeniable gap between the current AI agents and human experts.
Okay.
For those complex data analysis tasks, the ModelOff style ones, the best performing agent they tested, which was an integrated system, Autogen using GTC 4.0.
So a pretty advanced setup.
Right, one of the best combos available.
Right.
It only achieved 34.12% task level accuracy.
34%, that sounds low.
It is low, especially when you consider that based on sampled model-off competitions, human performance typically hovered around 64.06%.
Wow, okay. That's nearly a 30-point difference in
A
accuracy.
huge deficit, yeah. Between the best AI setup they tested and average human experts in strategic data analysis.
Okay, what about the other side? The even more complex end-to-end data modeling challenges from Kaggle, using that RPG metric.
Similar story, maybe even starker in some ways. For data modeling, the best agent achieved an RPG score of 34.74%.
Still in the mid-30s.
Yeah. While the measured human expert performance on those tasks was significantly higher, benchmarked at 65.02%.
65%. Again, roughly double the AI's performance.
The performance gap is just persistent across both types of tasks. It really shows the AI is currently, well, nowhere near competing with an average human expert in either deep analysis or complex modeling.
Now, you mentioned the best performer was an integrated system, like AutoGen with GPT-4o. And the paper notes these systems consistently did better than just using the base GPT-4o model on its own. What does that tell us?
Yeah, that's a crucial insight, actually. It confirms that the agent architecture itself matters.
Meaning the part that uses tools.
Right. The ability to access tools, to execute code, to iterate within an environment that does help. It allows the underlying LLM to translate its reasoning into tangible actions and get feedback.
So the tooling helps bridge the gap a bit.
It helps, yes. But the key finding is that the fundamental performance gap remains vast. Even with the tools, the AI is struggling with the core strategic elements of data science. It suggests the problem isn't just about, mechanical execution of code. It's deeper. It's about the conceptual understanding, the strategy.
Okay, so if the tools are helping somewhat, but the results are still way off,
Yeah.
the failure must be happening more in the strategic brain part of the AI, right? The reasoning.
That seems to be the case.
Did the researchers dig into why the agents were failing? What kinds of errors were they making?
They did. They did a detailed error analysis, and they cataloged these failures. And honestly, the errors reveal this kind of shocking lack of what we might call common sense, or the sort of intuitive grasp a human analyst develops pretty quickly.
Okay, like what? What were the major error types?
They highlighted 3 big ones. The most common was misinterpretation of data.
Misinterpretation. So the AI just fundamentally misunderstands what the data means.
Exactly. Think about confusing a column labeled year of record with a column that's clearly a unique voter ID.
Oh, wow.
The AI might make that kind of basic error because it seems to prioritize syntactic patterns. Oh, these look like numbers in a sequence, over the actual semantic meaning given by the column header or the context.
Right. It sees numbers that look like dates and thinks they are dates, even if the header says ID.
Something like that. It's the difference between being able to, read the words on the page versus truly understanding the document's purpose and meaning. A human would likely pause and question if they saw ID numbers incrementing at, years.
Yeah, you'd flag that immediately. Okay, so misinterpretation is one. What's the second failure mode?
The second is inadequate data identification.
Meaning it can't find the right data.
Yeah, the agent basically fails to identify and retrieve the necessary data file or table required to answer the question.
Yeah.
It seems to get overwhelmed by the multimodality, the long context, all the different pieces of input.
And just misses the crucial file it needs.
Right, which leads it to either just give up or maybe confidently state it can't compute an answer because it lacks the required input, even though the input was provided.
Frustrating. Okay, and the third major failure, you said it was maybe the most critical.
The third one really hits at the core strategy problem. Lack of problem-solving strategy.
Oh.
This is where the agent uses just completely incorrect approaches, wrong formulas, inappropriate modeling techniques for the type of data or question.
So not just coding errors, but fundamentally misunderstanding how to even tackle the problem.
Exactly. It reveals a deficiency not just in coding execution, but in that higher-level strategic thinking. The AI doesn't know how to set up the problem effectively in the first place, even if it could technically write code for a solution, just not the right solution.
This really sounds like that long, complex context we talked about, the 800 words, the multiple files. It's fundamentally breaking the AI's ability to focus and strategize.
It seems to play a huge role.
Did the researchers find that this context length affected the 2 different types of tasks analysis versus modeling differently?
Yes, they did.
Oh.
And it's actually a really fascinating paradox they observed.
Oh.
For the data analysis tasks, the model-off style, precision ones, the performance clearly dropped as the input context length increased.
So more words, worse results.
Pretty much. That massive 800-word prompt, plus maybe tables embedded in it, plus external files. It genuinely seemed to overwhelm the models. The more information they had to sift through, the worse their accuracy got.
The signal-to-noise ratio just killed their focus on the key details needed for the precise answer.
That's likely a big part of it. But here's the unexpected twist for the data modeling tasks, the Kaggle ones. The success rate did not show that same clear downward trend with longer input lengths.
Really? Why would that be?
Well, the researchers speculate that success in building a predictive model relies less on parsing every single word of a long narrative description, the how long, and more on correctly identifying and using the specific crucial data attribute information, like what columns are the features, what's the target variable.
Ah, the what?
Exactly, what they are supposed to predict and what data to use for it. If that core data description part is clear, the model seems better able to proceed with the modeling task itself, even if it's embedded within a lot of surrounding text. The overall length was less detrimental there. Hashtag tag outro.
Okay, so DSBench has definitely thrown down the gauntlet. It seems to have established itself as this brutally realistic, really challenging benchmark,
No doubt about it.
successfully incorporating that multimodality, the strategic complexity you find in real-world competitions like Model Off and Kaggle.
And the key takeaway, I think, is just undeniable. While these LLMs and the agents built on them are getting impressively good at the mechanics of generating code,
Yeah, they can write Python pretty well now.
they can. But DSBench really highlights how far they still are from achieving genuine data science expertise. The core gap isn't really about writing syntax anymore.
It's about the strategy.
It's about the strategic intelligence. It's that nuanced interpretation of ambiguous or messy data. It's the strategic application of tools across multiple complex steps.
And maybe just the common sense needed for that kind of multifaceted problem solving. That seems to be what's missing.
Completely. And it suggests that future progress, for AI agents in this space needs to focus not just on making the base LLM smarter,
Right.
but on fundamentally improving the agent system's ability to synthesize strategy, to interpret the messy real-world semantics of data, not just its structure.
The AI can learn the rules of code, but maybe it hasn't learned to be appropriately skeptical or insightful about the data itself yet.
That's a great way to put it. That skepticism, that insight, that's the hurdle that still separates the machine from a true data expert.
A really good thought to chew on next time an AI assistant offers you a confident prediction or analysis. We'll leave you with that challenge to think about.